So page 2 of complex numbers for the MHL, the MathHL chapter 16. So modulus is magnitude, and the argument is the direction of the vector representing a complex number. If the complex number is z equals a plus bi, the modulus z equals square root of a squared plus b squared. Modulus is basically like absolute value, but it works with complex numbers. Okay, so remember that this is just the hypotenuse of a Pythagorean theorem right triangle. So basically, since a vector can be written as or a complex number can be written as a vector, you can also find its length or magnitude by using Pythagorean's theorem. So here are a list of special properties of the modulus. So if you want to find the modulus of z conjugate, it's actually the same as the modulus of z, because basically remember that the modulus, if it points above the x-axis, the conjugate reflects below, so they both have the same length, which is basically what the modulus is, right? Modulus squared is equal to z times z conjugate. And basically the reason why that works is because of the, when you do FOIL with x minus y, x plus y, then the outside and the inside terms cancel out, and you're just left with the first and the last terms, like that. So basically that's the reason why if you multiply z times z conjugate, you end up with basically the square root of a squared plus b squared, okay? If you have z1 times z2 modulus, it's the same thing as taking the modulus of each thing individually and multiplying them like that, okay? And that kind of logically follows from what we learned in our investigation, right? If you have all these complex numbers multiplied together and finally take the modulus at the end, it's the same thing as taking the modulus individually of all of them and multiplying them together. And that is for any positive integer. Same thing works with division, okay? The z1 divided by z2 modulus is the same thing as z1 modulus divided by z2 modulus. Okay, provided that z2 is not equal to 0, because if z2 is 0, then the whole thing would be infinity. Okay, all right. Find modulus of z for z equal to 3 minus 4i. So 3 minus 4i, if we were to draw that on an Argand diagram, that would be 3 to the right and 4 down. Okay. Now remember, if you have a 3-4 sided triangle and that's a right triangle, you know that the third side is 5 because of the 3, 4, 5 right triangle, right? So the modulus for a would, of course, be 5. What about negative 8 plus 2? So negative 8 would be going to the right, or going to the left, 8, plus 2, you're going up 2. So you have 2. I think that was a very dumb place to write negative 8. Let's put it there. Okay, so to find the hypotenuse in this case, we would square the 2, square the 8, and then we would add them together and square it. So it'd be square root of 68, right? Square root of 68. What about the modulus of negative 4? Well, that would just be 4, right? Because it's just a flat triangle that goes to the left, 4 units. Well, the modulus is the length of that, which is 4. Okay. Number 2. If z is 2 plus I and w is negative 1 plus 3i, find. So the modulus of z would just be the modulus of 2 plus I. 2 plus I, the modulus would be square root of 2 squared plus 1 squared, which is equal to 4 plus 1 square root. So that would be square root of 5, right? What about z conjugate modulus squared? Well, z conjugate would be, instead of 2 plus I, it would be 2 minus I, right? So let's write out 2 minus I, and then we modulus that and then square it. So if we modulus 2 minus I, that would be equal to the square root of 2 squared plus 1 squared. And we're going to square that. Okay? So that would be square root of 5 squared, which is equal to 5. What about E? Z multiplied times W modulus. So that would be 2 plus I times negative 1 plus 3I, and that would be equal to negative 2, and negative 3 would be the real part, because 3I times I is 3 times negative 1, which is negative 3. And then we'll add it to the imaginary part, which would be negative I, but we don't need to like put negative I, we just put negative 1 because I already put the I here. Negative 1 plus 6. Okay, and then we'll combine these. So it'd be negative 5 plus 5I. Okay? All right, let's look at G. So in G, we're going to take Z divided by W. So it would be 2 plus I divided by negative 1 plus 3I. And if you remember, the way we simplify this into an expression with just A plus BI in the numerator is we can multiply by the conjugate, the complex conjugate. If we multiply by the top and the bottom by complex conjugate, it's fine because it's like we're multiplying by 1. And the bottom part becomes negative 1 squared, which is 1, minus 3I squared, which would be 9, or negative 9. So it would be plus 9. And the top would become, let's see, negative 2 minus 6I, and then it would be negative I, and then I times negative 3I would be positive 3. So let's see, the top would be 3 minus 2, which is 1, negative 6I minus I, which is negative 7I, divided by 10. So that would be the same thing as 1/10 minus 7/10 I. Okay, and that was for G. What about L? Oh, I'm sorry. What about I? So I is Z squared, which would be 2 plus I squared, which is equal to 4 plus 4I. And what's I squared? I squared would be minus 1. So it would be equal to 3 plus 4I. And that is Z squared. So what is Z squared modulus? It would be 3 plus 4I modulus, which would be equal to 5, right? Because if you have a 3, 4, 5 triangle, the 5 is the hypotenuse. Modulus Z cubed. So if I take the modulus of Z, that would be square root of 2 squared plus 1 squared, which is square root of 5. Okay, and then if I cube that, it would be 5 to the 1/2 cubed, which would be equal to 5 to the 3/2. Okay, all right. Number 3, prove that all. Oh, there's an example here, example 5 in the middle of this section. Prove that for all complex numbers Z, Z modulus, or Z conjugate modulus is equal to Z modulus. So let's define first that Z is equal to A plus BI, where A and B are real numbers. Then Z conjugate would be A minus BI, and if we modulus that, we're saying that it's going to equal to the modulus of Z. So the modulus of A minus BI is the square root of A squared plus negative B squared. But you can see that this would simplify to A squared plus B squared because negative B quantity squared is the same thing as b squared. And if you have square root of a squared plus b squared, well, isn't that the definition of the modulus of z? So we have shown that the z conjugate modulus is indeed equal to z modulus. Okay, what about z modulus squared equals z times z z conjugate? Let's see if we can prove that. So remember, let's see, we'll make z equal to a plus bi. So z modulus is square root of a squared plus b squared, and we're going to square that, and that gives us a squared plus b squared. Okay. Well, if we have a squared plus b squared, isn't that equal to a minus b times, or a minus bi times a plus bi, right? And if we know that that's equal to a minus bi times a plus bi, then we know that it's equal to z and z conjugate, because a plus bi is defined to be z, and then a minus bi is, of course, z conjugate. So we've shown, it's like either way it works, right? So z conjugate z and z conjugate are both going to equal a squared plus b squared. Okay, so there's our proof for that. Number 4, find the magnitude or the modulus of z given that z is equal to cosine theta plus I sine theta. Well, remember, if this is a and this is b, then we know that the modulus of z is actually equal to square root of a squared plus b squared, so it would be equal to square root of cosine squared theta plus sine squared theta. And sine squared theta plus cosine squared theta, remember the identity is equal to 1. So actually the whole thing is equal to 1. What about this one? So if we find the complex, the modulus of this z, let's see, probably the best way to do this is to distribute the r. So I have r cosine theta plus I r sine theta. Okay, and r cosine theta is my a value, r sine theta is my b value, so I could write the modulus equation as this, right? And I can simplify it by, let's see, I could factor out r squared, and then I would have cosine squared theta plus sine squared theta. And so the r squared on the outside is the square root of r squared, and cosine squared plus sine squared is equal to 1, right? So we basically end up with r times 1. So we know that the modulus of z is just r. Which totally makes sense, right? Because this is a vector, and the vector is a triangle with angle theta, and both the horizontal component and the vertical component are multiplied by r, so the hypotenuse, which is originally 1 because of the unit circle, is now r. Okay, so that's it for page 2.